Let's talk about some fictional chemistry from Project Hail Mary, or is it fictional? This video contains mild spoilers and is intended as an educational discussion of the science in Andy Weir's Project Hail Mary. If you haven't seen it or read it, I recommend it. The movie is a fairly close adaptation of the book, with some bits missing to shorten the story, of course. I'll only talk about the pieces I need for this video to try and not spoil the story any more than necessary. In short, the story is that the light from the sun begins to mysteriously dim. It is discovered that the cause is a bizarre microorganism dubbed astrophage. These microorganisms are completely black, absorbing broadly across the electromagnetic spectrum. Astrophage absorbs tremendous energy from the sun and shuttles back and forth from the sun to Venus. On Venus, it harvests CO2 from the atmosphere that it needs for reproduction. Everyone on Earth is doomed if we don't do something in the next few decades. The story follows Ryland Grace, a burnt-out PhD researcher teaching high school science, who was recruited because he once wrote a paper that intrigued the director of an international program to deal with the dimming sun. Astronomers discovered that virtually all of the stars in our vicinity had the same problem as our sun, except one, Tau Ceti, which is 11.9 light-years from Earth. Grace and a few others are sent on a spaceship called the Hail Mary to find out why Tau Ceti seems immune in hopes of finding a way to save the sun. The ship is named Hail Mary because it's unlikely to work. I mean, what if the astrophage is there, but the dimming isn't detectable yet? Nevertheless, this Hail Mary, full of grace you'll notice, is sent there to power the ship. They use the astrophage themselves because it is an extremely dense form of energy. One cell of the stuff absorbs 1.5 megajoules of energy and gains 17 nanograms of mass because E equals mc squared. 1 gram of the stuff is then 9 times 10 to the 13 joules. For comparison, 1 gram of astrophage has the energy of about 7 billion AA batteries, which would weigh 161,000 metric tons, or about 50 million ham sandwiches, or about 750,000 gallons of gasoline. Hard to beat mass to energy conversion for energy storage. Astrophage is found to use DNA and proteins the same as organisms on Earth, but somehow it does direct energy to mass conversion, allowing it to store massive amounts of energy. Using this fuel, the astronauts head to Tau Ceti, reaching a speed of somewhere between 92% and 99.5% of the speed of light. Because of the relativistic speeds obtained, they make the trip in about 4 years from their perspective, but 13 years pass on Earth. To make the trip, the astronauts are put in hibernation, and Grace is the only one who survives the process. So he is alone in a different solar system trying to save the Earth. Well, he's alone until he meets an alien from a different solar system trying to do the same thing he is. They discover the reason why the star Tau Ceti is unaffected isn't because astrophage isn't there. It's because there is an organism in the atmosphere of a planet that the astrophage visit to pick up CO2 and reproduce that eats astrophage. A natural predator of the astrophage dubbed Taumoeba, a portmanteau of Tau Ceti plus amoeba because it looks and moves like an amoeba. Because the astrophage have a natural predator here, their population is controlled and Tau Ceti is spared significant dimming. The solution is then to take Taumoeba to Venus to control the astrophage population in our solar system. Here's one of the weirdest things. Taumoeba lives on a world that is 91% CO2, 7% methane, 1% argon, and then 1% trace gases. So there's little N2 in the atmosphere. Grace discovers that the Taumoeba are sensitive to nitrogen, a fairly bizarre phenomenon, but also a major problem for Venus's atmosphere, which has 3.5% nitrogen, which kills the life form instantly. Why is it bizarre, chemically speaking, that something would find dinitrogen toxic? How do organisms do chemistry with dinitrogen on Earth? Why might Taumoeba be killed by high dinitrogen concentrations despite needing nitrogen compounds like DNA and amino acids for their biology? I'll give my theories here partially as a way of talking about the chemistry of dinitrogen. The reason I call the dinitrogen toxicity in the book bizarre is because dinitrogen is quite inert. Chemists usually talk about strategies for activating dinitrogen. It tends to not react with most things. It's cheap, and purified nitrogen is a good way to drive out reactive oxygen from reaction vessels. Lithium is the only element that reacts with N2 at room temperature and 1 atmosphere pressure, but we can design compounds that will react with N2. Here is one such compound with iron from the Peters group at Caltech, which was used to make ammonia catalytically. There are quite a few examples of dinitrogen reactivity with iron complexes now. Here's a few other examples where dinitrogen reacts with metal centers. One complex is a heterodinuclear example with uranium and molybdenum I prepared as a grad student with Kit Cummins and Polly Arnold. Here's another example prepared by Peter Scott and coworkers where uranium reacts with dinitrogen in a side-on fashion. And here's one more from the Cummins group where a molybdenum complex splits into two molybdenum nitrides. I chose examples with iron, molybdenum, and uranium because these three elements hold a special place in how nitrogen gets converted to ammonia. There are several natural enzymes called nitrogenases that do this reaction, the most active of which has both iron and molybdenum at the active site. The heart of the enzyme is this sulfide cluster with 7 irons, 1 molybdenum, and a carbide at the center. Yes, the best data we have suggests that's a carbon atom at the center of the cluster. The overall reaction is an ATP-driven process that produces ammonia and hydrogen. The Haber-Bosch reaction is the industrial method we use to produce ammonia from nitrogen for fertilizers and other applications. The reaction was discovered by Fritz Haber, a brilliant and by many accounts an evil guy. I would say his legacy is definitely complicated, as we'll see. He developed the ammonia synthesis to help the Germans in World War I, who were running out of nitrogen compounds for munitions. Haber also helped the Germans develop and implement chemical weapons for the battlefield. He also developed Zyklon B, the poison used in the gas chambers of the concentration camps during World War II. For the ammonia synthesis, Haber discovered that uranium was one of the most effective elements, along with some precious metals like ruthenium and osmium. Carl Bosch was also a German, and he turned the Haber process into a large-scale industrial process and found an iron-based catalyst for the reaction. Later, Bosch became head of the massive German chemical company IG Farben. When the Nazis came to power, they began firing all of the people of Jewish descent in the company, and Bosch protested. Because of his protests, he was gradually sidelined in the company and later had to step down. The amount of ammonia we make every year is staggering. In 2009, we made 130 million metric tons of ammonia, mostly for fertilizer. That's about 1,500 Washington monuments, or greater than 21 times the weight of the Great Pyramid of Cheops in a single year. We as humans can't fix nitrogen, so 100% of the nitrogen in our DNA, proteins, etc. comes from what we eat. And it is estimated that about half of the nitrogen we consume comes from the Haber-Bosch reactors. Put another way, the population of the Earth could only be about half of what it is without this one reaction. But how does Taumoeba get its nitrogen if there's none in the atmosphere? The book doesn't really say anything about this issue, but the organism has to get it from somewhere. We can speculate that it gets it from the same place we do, which is from our food. Taumoeba's food is astrophage, which can make matter from energy. Astrophage, in principle, could make any matter it needs for survival, but making things other than hydrogen is more energy intensive. The energy is first used to generate particles, nucleons, and electrons. Because hydrogen's nucleus is just a proton, there's no nuclear binding energy released when hydrogen is formed. For every other element where there are multiple nucleons, the energy will be released when the nucleus forms, and if the organism doesn't recapture that energy, it's lost. This can be calculated using the mass defect fraction, which is this, where Be is the binding energy and A is the mass number. For example, to make an atom of nitrogen-14, the binding energy equals 104.66 MeV. So the calculation goes like this. So a little less than 1% of the energy is lost making nitrogen. The calculations are similar for carbon-12 and oxygen-16. Around 0.8 to 0.9% is lost. Nevertheless, nitrogen has to come from somewhere, and the most obvious place to get it for astrophage is from the energy to mass conversion. So we can postulate that Taumoeba gets its nitrogen from food, but why would dinitrogen be toxic? We don't really know enough about the biology to say for sure. But what if Taumoeba has high energy machinery for carbon dioxide reduction? Thermodynamically, N2 reduction to ammonia is more favorable than CO2 reduction to something like formate. Dinitrogen is kinetically more difficult to react, but if the enzyme it used was unselective, it might reduce dinitrogen as well. After all, it lives in an environment with little to no nitrogen gas. This lack of selectivity isn't unheard of. For example, earth nitrogenases will reduce CO2 to formate. The reverse could happen if the enzyme's active site was able to bind dinitrogen, even a little. Many organisms find ammonia to be toxic, including humans. In order to assimilate ammonia, many organisms shuttle the compound towards amino acid synthesis like glutamine and glutamate synthesis pathways. When Gray selectively breeds a strain of Taumoeba that can survive with some nitrogen, he may have been selecting for organisms with upgraded glutamine to glutamate synthesis pathways. There is one possible theory why Taumoeba could be sensitive to dinitrogen despite the compound usually being inert. Andy Weir did a great job of world building, and there are plenty of videos on the physics discussed in the books. There's my theory on this chemical issue. Feel free to put your theory in the comments or let me know what you think where I'm going wrong. Again, if you haven't read the book or watched the movie, words of encouragement. Thanks for watching. We make these videos for fun and to give back to the community. Please subscribe, give us a thumbs up, and take a look at the rest of the playlist, which has a variety of videos at a variety of levels. Hit notifications so you don't miss anything, because we only drop vids occasionally. Thanks.